Hello everybody. Today we are going to talk more about telescopes, specifically about different designs of telescopes that are generally used. We will talk about three important designs in this video. Remember, in the earlier videos, the link you can see on the top, we had talked about a refracting telescope which has been traditionally used, the first telescope that was ever made, which has basically lenses. We also talked about a reflecting telescope which used something called as a reflecting element or a mirror. We saw how the aperture or the size of the mirror helps us in gathering more light and gives us more resolution. In this video, we will talk about some other designs of telescopes. As you can see here, in a general Newtonian reflecting telescope, you have a primary mirror which is a reflecting element at the bottom of the tube, and then there is a secondary mirror sitting here at an angle of 45 degrees which helps us push the rays out of the telescope, where we have an eyepiece and we look at the object through the eyepiece. Now, as you can see, this telescope is pointing towards the sky or towards a celestial object in this direction, whereas we are looking at the object at an angle which is normal or perpendicular to the line of sight. Slightly inconvenient design, right? Hence, people came up with a new kind of telescope, new design of telescope. Cassegrain is the name of that telescope. So, here you can see, just like a Newtonian reflector, even this telescope, the Cassegrainian telescope, has a reflecting element at the bottom of the tube. This is the primary mirror, parabolic in shape. The mirror has a hole at the center, and you can see in this image the eyepiece can be attached at the end of the tube. So, now you are looking more or less in the direction of the source. An important difference here is, apart from the hole at the bottom of the tube, is the secondary mirror. In the Newtonian telescope, the secondary mirror was a flat mirror at an angle of 45 degrees to the optic axis or the primary axis of the primary mirror. Here the mirror is a hyperbolic secondary mirror. Okay. So, what happens is, the light rays which are coming from a distant source, they get focused at some point, but just before that you have a hyperbolic secondary, and because of this hyperbolic secondary, now the focus shifts to this point. So, what you have done is effectively folded the light rays on themselves, and the advantage of this design is, apart from looking in the direction of the source more or less, you have effectively reduced the size of the tube and also can get an effectively large focal length. So, a larger focal length with a reduced size of tube is what Cassegrain telescope gives us. Alright, remember, it has a parabolic primary and a hyperbolic secondary mirror. What are these different mirrors and what are the uses of different shapes of these mirrors? So, we know that we have different conic sections. So, there is a parabola, there is a hyperbola. Okay. So, what is an hyperbolic mirror? If I take the hyperbola and rotate it, okay, in 3D, I will get a hyperbolic structure. So, a part of this hyperbola will give me a hyperbolic mirror, similar to what the parabolic mirrors are. General examples in our day-to-day life, we see these kind of mirrors on turnings of roads. These are spherical mirrors. These mirrors are a part of a sphere. Okay, they give us a wider field of view. On the other hand, dish antennas or the satellite dishes that you have for various TV shows which you watch on these direct to home channels use a parabolic dish or a parabolic reflector. Then there are some hyperbolic mirrors. You can see the structure of this mirror is more or less like an hyperbola. Okay. There are advantages of each and we will see them now. So first is spherical mirror. The problem with spherical mirror, as we have already seen in an earlier video, you can see the link at the top, is they have spherical aberration. They also have something called as coma and astigmatism. So what are these things? So spherical aberration is because you can see here there is a lens and it is showing that all the rays do not come at exactly one point, right. Then you have coma in such mirrors. That means the objects which are towards the periphery, they will appear like this, like an extended thing, which, let us say if it is a star, it looks like a tail like structure has been added to the star, especially the stars which are at the periphery of the field. Then there is something called as astigmatism. So you have a nice image, let us say AIO written here. If there are imperfections in the making of the mirror, you may have a shift in focus along the lateral side or a horizontal side or a vertical side of that mirror. So if the mirror is not a perfect parabola or a hyperbola or a perfect sphere, along one of the axis the focus is going to shift obviously, right. So this is called as astigmatism. So a spherical mirror has all these issues and hence to improve we go for a parabolic mirror. Parabolic mirror removes the spherical aberration, but the coma and astigmatism still remains, and there comes the hyperbolic mirror where you more or less get rid of coma, but astigmatism may still remain. I am not saying that hyperbolic mirror, if I can make a hyperbolic mirror, I will get a perfect image. There will be some higher order coma effects which we will not talk about in this video, but whatever problems a parabolic mirror or a spherical mirror can give, those problems are more or less solved in hyperbolic mirrors. The other advantage of hyperbolic mirror is because of its structure we get a larger field of view of the sky for a same size of the mirror or same aperture. This is an important advantage. Keeping in mind this advantage, a new variety of telescope, a new model of telescope or a new design of telescope was made, and it is called as the RC or Ritchey-Chrétien telescope. It is basically the Cassegrain telescope with a minor difference, and that is now the primary mirror is no longer a parabolic mirror but a hyperbolic mirror. So now you have two mirrors, a hyperbolic mirror as the primary mirror, a hyperbolic mirror as the secondary mirror, and the design remains same just like the Cassegrainian telescope. The advantage, as we saw, a reduced coma and an effectively higher field of view. So this is a very important design and you will shortly come to know why. So this to my right is one of the most famous telescopes in the world, the Hubble Space Telescope, which is orbiting the Earth. Hubble Space Telescope is again a RC design, RC telescope, which has a hyperbolic mirror, primary mirror and hyperbolic secondary mirror. Remember, since these both are mirrors, there are no lenses involved, such telescopes can also be used at other wavelengths. If I simply replace, if I simply attach a UV detector or a UV CCD, ultraviolet CCD, a CCD that actively detects ultraviolet rays or infrared rays, I can have them here and I can get images in those particular wavelengths. Of course, not the entire range, it depends on what kind of mirror, what kind of reflectivity these mirrors have, those ranges of wavelengths. Yeah. Here on the other side, to my left here, we have another telescope which is being used and this is the Devasthal optical telescope present in India. So, this is again an RC design. Many telescopes, if you just search for Ritchey-Chrétien telescopes, you will see many professional telescopes, many big telescopes employ these kind of designs, that is they have a hyperbolic primary and a hyperbolic secondary. There is another improvement. Such telescopes are nowadays readily available for amateur astronomers and in various places commercially available telescopes. These are and you, I am sure many of you have already heard this name, that is the Schmidt-Cassegrain telescope. This is basically Cassegrain telescope with a spherical mirror and a correcting plate at the start of the tube called as the Schmidt correcting plate, which also has another hyperbolic mirror here, which is the secondary mirror. The advantage of this design is you cover the aperture of the tube, that saves both your primary and secondary mirror from dust or moisture or any other issues. And the important use of the correcting plate is to correct spherical aberration. So, you have a Schmidt correcting plate something like this, which is fixed at the opening of the tube of the telescope, on which sometimes you have the secondary mirror attached, and with the help of this tube, if you have a spherical aberration, the tube is such that it will slightly deflect the rays and make sure that the spherical aberration is removed. So, this is another beautiful design which is commercially available, and easily you can go and buy these telescopes, okay, called as the Schmidt-Cassegrain telescope, which comes with a corrector plate. Lastly, we will talk about an important design in telescopes which is called as the Coud focus. It is also sometimes called as the Nasmyth focus. Remember, when you have huge telescopes like a 10-meter telescope or an 8-meter telescope or 2-meter telescope, let us say such huge telescopes which are in meters, the primary mirror has diameter in meters, they are huge, they are heavy, they are difficult to maneuver, and balancing these telescopes on mounts becomes a tricky job. Also, one has to remember, you do not go and look through the telescope with your eye, but rather what you would like to do in such telescopes is, you want to record the image, you want to record the spectra, you want to expose the telescope to the sky for a longer time so that you see fainter and fainter objects. So, you want a recording device like, let us say, a photographic plate in the older times, or a CCD, or a spectrograph and a CCD. These things are bulky. The spectrographs, the CCDs, they are bulky because the CCDs need to be cooled, hence you have to attach a coolant to the CCD. The spectrographs are bulky, they can be few tens of kilograms, and once you attach them, the center of mass of these telescopes may shift, and hence balancing them will be again a difficult issue. So, for that we have a very beautiful design in which what we do is, we have a Cassegrainian kind of telescope, okay, and now let us say this is a parabolic mirror, I have an hyperbolic mirror here, okay, this is the focus of the telescope which is now effectively at this point. So, here I will have to attach my CCD or camera or a spectrograph or whatever, and this will tilt the balance of the telescope, but there is something smart that can be done. You attach a flat tertiary mirror, this is the third mirror now you have, a mirror such that I can rotate this mirror along a particular axis and push the rays out in the direction I want, and at this particular fixed point I can have my recording devices like spectrographs, CCD cameras and spectrographs, etc. So, this is called as the Coud or Nasmyth focus. How does this work? So, here you have a primary, you have a secondary, you have a tube, and there is a rotatable flat okay, the tertiary mirror that we talked about. And this rotatable flat can rotate, like if you move the telescope in a particular direction, you can rotate it and get the rays out along the polar axis of the telescope. Okay, what is polar axis or what are the declination axis? We have talked about this in the videos of mounts. Here is another beautiful image from nice page. This is the telescope. This is the mount of the telescope. Here is the primary, here is the secondary, here is the rotatable flat, and you can see that the light rays are pushed out from the rotatable flat along the polar axis, and you can have your spectrographs or CCD cameras sitting right here, so that no matter how you move the telescope, just move the rotatable flat, get your images or light rays at a particular spot. I hope you found this video interesting. There are many designs of telescopes right now being used, which help us reduce various effects, help us ease our life, help us ease our observations, and you can read more about them on the internet. Thank you so much.